How did a people without concrete, without industrial sawmills, without chemical preservatives, manage to build wooden ships that crossed the North Atlantic and hulls that endured centuries of cold, damp air? While much of our modern lumber struggles to last a lifetime, the contradiction is not romantic exaggeration. Archaeological timbers from Viking ships, waterfront settlements, and rural farmsteads have survived in environments that should have consumed them. Yet contemporary treated wood, kiln-dried and factory-sealed, often fails within decades. The assumption that technology moves in a straight ascending line becomes difficult to defend when faced with this evidence. Something in the Viking approach to material, moisture, and limitation operated differently. This investigation begins not with admiration, but with a question that unsettles modern confidence. What did the Norse understand about wood, water, and time that we no longer practice? A common belief holds that Viking durability was simply a matter of massive trees, that ancient forests provided superior timber unavailable today. The image is compelling: towering oaks rising from primeval Scandinavian forests, felled and transformed into ships destined for legend. Yet size alone does not explain resilience. Density and age matter, but they do not account for why certain Viking planks endured mechanical stress and biological attack for centuries. Dendrochronological and structural analyses of vessels such as the Oseberg and Gokstad ships reveal a more disciplined logic at work. Many hull planks were not sawn into shape. They were radially split from the log, following the natural orientation of growth rings. When wood is cleaved along its grain, the fibers remain continuous from one end to the other. The cellular tubes that once carried sap are not severed across their length. They remain aligned, intact, and structurally coherent. Sawing, particularly under the pressures of industrial production, interrupts that continuity. A blade slices indiscriminately through fibers, creating exposed end grain and microscopic fractures. These fractures are not visible to the naked eye, yet they serve as pathways for moisture migration and as entry points for fungal colonization. Over time, these internal disruptions accumulate stress. In cold seawater or damp air, that stress translates into weakness. The Norse technique reduced internal strain before the wood ever touched salt water. A split plank retains the natural tension of the tree in a balanced state. It bends more predictably. It resists delamination. It absorbs shock without tearing across compromised fibers. This was not mysticism. It was material literacy earned through generations of observation and repair. Viking shipwrights did not force wood into geometric convenience. They followed the growth pattern of the tree and allowed structure to emerge from biology. Modern efficiency maximizes yield per log and speed per hour. Viking efficiency maximized structural integrity per plank and longevity per vessel. The distinction appears subtle at first glance. It becomes unmistakable when centuries pass and the evidence remains. Another popular claim suggests that Viking wood was cut according to lunar cycles, that felling trees during a waning moon reduced sap content and guaranteed exceptional longevity. The idea carries a certain poetic appeal. It places shipwrights beneath a winter sky, measuring their labor against the phases of the moon, aligning timber with celestial rhythm. Variations of this belief appear across European folk traditions and continue to surface in modern marketing under the name of moonwood. Yet, when examined under controlled scientific testing, the lunar hypothesis struggles to demonstrate consistent structural advantages. Large-scale forestry studies have measured density, shrinkage, and durability in timber cut at different lunar phases. The results have not supported the claim that the moon alone alters wood in ways that significantly affect long-term performance. The romance of the theory exceeds its measurable impact. What can be documented with far greater clarity in Viking contexts is seasonal awareness rather than lunar superstition. Trees felled in winter, when temperatures drop and metabolic activity slows, contain naturally reduced moisture content. Sap flow diminishes as growth pauses. Carbohydrate transport decreases. The wood enters a state closer to dormancy. Cutting during this period reduces internal water load and limits the dramatic shrinkage that occurs during subsequent drying. Winter-felled timber therefore stabilizes more predictably. It twists less. It checks less severely. It carries lower risk of internal stress fractures that later invite moisture and decay. In the North Atlantic climate, where construction windows were narrow and drying conditions variable, this practical timing mattered. The sagas and later Scandinavian forestry customs reflect this awareness. They reference winter cutting as common practice, not as ritual obedience to celestial symbolism, but as alignment with climatic reality. The paradox dissolves once observation replaces folklore. Viking builders were not indifferent to cycles. They paid close attention to biological rhythms embedded in the landscape, but their decisions followed ecological timing more than cosmological belief. The forest itself set the schedule. The moon may have been visible overhead, but it was the physiology of the tree that determined when the axe fell. It is often assumed that Viking ships survived because they were simply massive, that thickness alone protected them from the violence of the North Atlantic. The image of a heavy hull cutting stubbornly through storm seas feels intuitive, yet clinker construction reveals a far more sophisticated logic. The Viking hull was not built as a rigid shell. It was assembled from overlapping planks, each one carefully shaped and fastened in sequence so that the edge of one board lay over the next. Iron rivets and clenched roves secured the layers, but they did not fuse them into immobility. Instead, they created a lattice of controlled movement. The hull could flex. It could yield slightly under pressure without surrendering structural coherence. When a wave strikes a rigid surface, force concentrates. When a wave strikes a flexible one, force disperses. Clinker construction allowed stress to travel along the length of the vessel, shared across hundreds of seams, rather than absorbed at a single fracture point. This distributed resilience reduced catastrophic failure. A cracked plank could be replaced. A loosened rivet could be reset. The ship was conceived as a living system of parts, not as a monolithic object. Even the iron rivets deserve close scrutiny. Much Viking iron was smelted from bog ore, a resource abundant in Scandinavian wetlands. This iron often contained measurable levels of phosphorus. In certain cold and low-oxygen marine environments, phosphoric iron can exhibit improved resistance to corrosion compared to purer forms of later industrial steel. Archaeometallurgical analyses of surviving fasteners indicate that these rivets endured prolonged exposure to brackish water with surprising stability. The Norse did not possess electrochemical theory. They did not calculate galvanic potentials or corrosion curves. Yet through repeated use and observation, they recognized which metal survived maritime exposure and which deteriorated too quickly. Selection was empirical. Failure was a teacher. Materials that endured were retained within tradition. Their ships were not indestructible. They required care, tar application, plank replacement, and seasonal maintenance. But they were designed with this reality in mind. They worked with motion rather than against it. They accepted the sea as a dynamic partner rather than an adversary to be overpowered. In that acceptance lay their true durability. In settlements across Iceland and Greenland, another assumption quietly persists. Survival in Arctic climates is often attributed to toughness alone, as if endurance were a personality trait rather than an engineered condition. The image of fur-clad settlers braving endless winter has overshadowed the architectural intelligence embedded in their dwellings. Yet excavations at sites such as Brattahlíð reveal a different story, one rooted not in defiance of climate, but in measured cooperation with it. Turf architecture was not an improvised shelter of necessity. It was a calculated system. Blocks of sod were cut with precision and stacked over timber frameworks, then reinforced with compacted earth. These thick earthen walls created substantial thermal mass, absorbing heat slowly and releasing it just as gradually. Interior warmth from hearth fires did not dissipate abruptly into the Arctic air. It was moderated, stored, and redistributed. The result was not perfect insulation in the modern sense. It was stability. Thick turf walls buffered temperature swings that would otherwise shock exposed timber. Rapid expansion and contraction, common in heated modern interiors where forced air systems create sharp humidity gradients, rarely occurred within these Norse dwellings. Moisture levels rose and fell with the seasons, but they did so gradually. Wood, embedded within layers of turf, remained shielded from sudden moisture oscillation, one of the primary drivers of fungal decay. Fungi thrive where conditions fluctuate sharply between damp and dry. They exploit stress fractures and internal tension. In Viking houses, variation existed, yet it unfolded over weeks and months rather than hours. The structure breathed with the landscape. Modern heated homes often create artificial extremes. Indoor air dries rapidly in winter, then humidifies in summer. Timber reacts internally to these abrupt shifts. Microcracks form, stress accumulates. The Viking dwelling experienced cold and damp, but the transitions were slow enough to prevent internal rupture. Stability, not dryness, preserved the structure. The Norse managed microclimate through layering rather than mechanical intervention. Turf, timber, earth, and air worked together as a composite system. They accepted slower seasonal rhythms instead of attempting to override them. In doing so, they reduced strain at the material level. Their resilience was not a matter of heroic endurance. It was the quiet outcome of respecting environmental pace. The idea that Vikings relied solely on raw timber overlooks one of the most consequential preservative technologies of the North Atlantic world: pine tar. Archaeological surveys across Scandinavia have identified extensive tar production sites, some consisting of large pit kilns capable of generating significant quantities in a single burn. These were not isolated household experiments. They were organized operations, structured to support shipyards and fleets. Tar was not incidental to Viking expansion. It was infrastructural. Pine tar is produced through the slow pyrolysis of resin-rich wood, typically pine roots and stumps, in low oxygen conditions. The process separates volatile compounds from the wood and condenses them into a viscous liquid, rich in phenolic substances and natural biocides. When applied warm, tar penetrates deeply into wood fibers. It displaces water, saturates cellular structures, and creates a hydrophobic barrier that reduces capillary moisture uptake. Yet tar does not seal wood in the way modern synthetic coatings often do. It allows limited vapor exchange. This breathability is critical. Completely impermeable layers can trap moisture within timber, creating internal conditions ideal for fungal growth. Tar, by contrast, discourages colonization while permitting gradual drying. It modifies the surface environment without isolating the interior from seasonal equilibrium. Ships were retarred regularly. This was not an admission of failure. It was recognition that preservation is an ongoing relationship between material and climate. Maintenance was embedded in maritime culture. Crews understood that endurance required return and renewal. The paradox is instructive. The Viking world invested labor continuously in preservation. Time and effort were allocated not just to building, but to sustaining. Modern systems often pursue the illusion of permanence through one-time treatments designed to eliminate future attention. Viking durability emerged from repetition. Longevity was not a single chemical event. It was a practiced ritual of care, renewed as predictably as the tides themselves. There is also the matter of leaching and nutrient removal, a quieter process that rarely receives attention outside material science. Freshly cut timber is not inert. It carries within its cellular structure sugars, starches, and hemicellulose that once sustained the living tree. To fungi, these compounds represent accessible energy. Moisture alone does not create decay. Moisture combined with food does. Evidence from multiple medieval European contexts indicates that immersion in water, brine, or alkaline solutions could reduce the concentration of these soluble nutrients. While documentation specific to every Viking shipyard is understandably incomplete, maritime communities across northern Europe practiced soaking planks prior to final shaping and assembly. Timber recovered from waterlogged sites often reveals chemical signatures consistent with prolonged exposure before installation. The mechanism requires no mysticism. When wood is submerged, water penetrates its porous structure and dissolves certain soluble carbohydrates. Over time, diffusion carries these compounds outward into the surrounding liquid. In brine, osmotic gradients may further influence the movement of dissolved substances. In alkaline solutions derived from ash or lime, chemical reactions can break down hemicellulose into forms more easily removed. Coastal Viking settlements had ready access to salt water. Rivers and tidal estuaries provided environments where planks could remain submerged for extended periods. The process required patience rather than elaborate technology. As nutrients diminished, the internal environment of the wood changed. Fungi, encountering such material, would find moisture but less accessible food. Colonization becomes slower. Growth becomes limited. This approach reflects ecological reasoning rather than surface treatment. Instead of merely sealing the exterior and hoping the interior remains protected, the Norse altered the internal conditions that permit decay. They did not attempt to sterilize the world around their ships. They modified the microenvironment within the material itself. Remove the food source, and the organism struggles to thrive. The principle is biological and straightforward. Durability emerges not from magical additives, but from understanding what decay requires and quietly denying it those conditions. Drying methods further complicate any simple comparison between Viking timber and modern lumber. Industrial kilns were developed to solve a commercial problem. Builders needed predictability and speed. Moisture had to be removed quickly so that wood could be transported, sold, and installed within tight construction schedules. Controlled heat and forced airflow now reduce moisture content in days rather than months. From a production standpoint, this is efficient. From a structural standpoint, the consequences are more complex. When wood dries rapidly, the outer layers lose moisture first. They shrink while the inner core remains swollen. This imbalance generates internal tension. Microscopic fractures develop along growth rings and at the boundary between early wood and late wood. These microcracks are often invisible during installation, yet over time they become conduits for moisture infiltration and biological attack. What begins as accelerated preparation can quietly introduce long-term vulnerability. Historical Scandinavian practice moved at a different pace. Timber was stacked carefully above ground level, often on stones or raised supports, to prevent ground moisture from wicking upward. Spacers were inserted between layers to allow consistent airflow. Roofed sheds or partially shaded yards protected the wood from direct rain while permitting wind circulation. The objective was not to eliminate moisture instantly. It was to allow the entire cross-section of the beam to equalize gradually. Time functioned as part of the engineering process. A beam was not declared ready because it satisfied a shipment date. It was ready when its internal movement had settled, when shrinkage had occurred evenly, and when surface checking had stabilized. Seasonal rhythms reinforced this patience. Long winters limited construction activity. Summers offered drying winds, but not industrial urgency. The Norse did not conceptualize this as a virtue. It was simply the tempo imposed by climate and economy. What modernity calls delay, they understood as preparation. Their timber entered service with internal stress already resolved, not hidden beneath the speed of production. In that slower calibration between material and season lay a quiet advantage that only becomes visible when generations pass. It is tempting to romanticize Viking decline in Greenland as a simple story of climate defeat, as if colder winds alone erased an entire society. The narrative feels clean and satisfying. Temperatures fell, ice advanced, and settlements vanished. Yet the archaeological record resists that simplicity. What emerges instead is a more intricate interplay between adaptation and rigidity, between environmental awareness and cultural identity. As conditions cooled during the onset of the Little Ice Age, zooarchaeological evidence shows that Norse settlers adjusted their diet. Seal bones increased in household middens. Marine resources became more prominent. This shift suggests ecological flexibility. The settlers were not oblivious to changing conditions. They observed declining pasture quality and responded by expanding reliance on hunting and fishing. In this respect, they behaved as pragmatic frontier communities often do. Yet adaptation did not extend equally into every domain of life. Social hierarchy in Greenland remained strongly tied to pastoral ideals inherited from Norway and Iceland. Cattle ownership signified status. Church construction and imported goods reinforced connections to European identity. Even as marine protein sustained survival, cultural prestige remained anchored in landholding and livestock. Here lies the deeper paradox. The same attentiveness to material limits that guided shipbuilding and architecture did not fully transform social structure. Environmental signals were recognized, but identity exerted gravitational pull. Complete transition to a predominantly maritime culture may have required abandoning symbols of status and belonging that defined Norse self-understanding. Viking durability, therefore, was contextual rather than universal. It flourished when empirical observation governed technical decisions. It faltered when cultural continuity constrained adaptation. The Greenland story becomes less a morality tale of heroic failure and more a study in selective flexibility. Societies, like ships, survive when they balance firmness with movement. When flexibility narrows to certain domains while remaining rigid in others, stress accumulates. History does not condemn the Norse for this tension. It simply records the outcome. Their settlements endured for centuries in a marginal environment. That longevity alone testifies to considerable resilience. But resilience has thresholds. The lesson is not that climate conquers culture. It is that adaptation must reach beyond tools and timber into the deeper architecture of identity if it is to endure indefinitely. When the evidence is gathered and placed side by side, grain splitting instead of sawing, winter felling instead of arbitrary timing, flexible clinker hulls rather than rigid shells, pine tar treatments renewed season after season, gradual air curing instead of accelerated kiln drying, ecological siting instead of architectural dominance, a pattern begins to emerge. It is not dramatic. It does not rely on hidden formulas or supernatural timing. It is quieter than that. Viking success with wood arose from sustained attention to limits imposed by biology and climate. Trees grow in particular ways. Moisture moves through cellular pathways with predictable behavior. Fungi require specific conditions to thrive. Saltwater exerts cyclic stress rather than constant pressure. The Norse did not attempt to overpower these forces. They studied them through lived experience. They observed failure and adjusted accordingly. They accepted that maintenance was part of existence. Ships were retarred, planks were replaced, houses were reinforced. Durability was never imagined as permanence without return. It was understood as continuity sustained through repeated care. This perspective stands in quiet contrast to modern expectations of maintenance-free materials and one-time treatments designed to eliminate future attention. Modern technology offers extraordinary speed and scale. Lumber can be milled, dried, transported, and installed within weeks. Protective coatings promise extended performance with minimal labor, yet efficiency often distances us from intimate knowledge of how materials behave over decades. We calculate load-bearing capacity with precision, yet rarely witness the slow movement of wood across seasons. The Norse example does not demand regression into the past. It does not argue for abandoning contemporary engineering. It invites reconsideration of relationship. Durability begins at the moment of choice. It begins with how a tree is cut, how a plank is shaped, how fibers are respected rather than severed, how moisture is allowed to move gradually instead of being forced into submission. The remains of Viking timber are not monuments to invincibility. They are records of patient negotiation with a demanding world. They testify to a culture that understood resilience as partnership with environment rather than conquest of it. If there is something enduring in their legacy, it is not the image of expansion across oceans. It is attentiveness. Attentiveness to grain, to season, to salt, to time itself.